In the years preceding the development of relativistic theories by Albert Einstein, science had already made great strides to provide for its foundations. An early approach was established by Galileo Galilei in the 17th century by the Galilean Transformations. Galilean transformations were used to remodel between coordinates of two inertial reference frames. For instance, if we consider a train to be traveling with a constant velocity v, and two persons are sitting inside it who clap their hands with a non-zero time difference. If we see this incidence from within the train, we may say that the space separation is x and the time separation is t. If this same incident is observed from outside the train, the time separation remains the same. That is, t is equal to t prime. At least this is what we can assume for now. But what about the space separation? Does it also remain the same? Well, it doesn't. So let us take this new space separation to be x prime. By Galilean transformation, we find that x prime is equal to x plus vt or x plus vt prime. If the train was at rest, we would find that x is equal to x prime. By the principle of Galilean invariance, it can be stated that laws of physics hold true in all inertial reference frames. This can be validated by the idea that for force to remain constant, acceleration also needs to remain constant. So, if we consider an object with velocities v1 and v2 in two different reference frames, and the relative velocity between the frames be v relative, we can find that v2 is equal to v1 plus v relative. We already know that acceleration is the differentiation of velocity with respect to time. If we substitute the value of v2 and if we continue to assume that t1 is equal to t2 is equal to t, we may find that acceleration remains constant. That is, a1 is equal to a2. This may entice us, but there is a major drawback. For everyday speeds, it is highly accurate. But what about the speed of light? Can we still consider time to remain the same in all reference frames? Apparently, we cannot. This is the very point where the Galilean transformations are replaced by the Lorentz transformations. What Hendrik Lorentz brought to life was a factor given by gamma equal to 1 divided by 1 minus v by c squared, whole rooted. This was known as the Lorentz factor. He hence anticipated that if an object moves near the speed of light, then in different frames time can be given by t prime equal to gamma into t minus vx by c squared, hence giving x prime to be equal to gamma into x minus vt. The phenomena like time dilation, length contraction, relativistic mass, energy and momentum, and mass-energy equivalence can be deduced by the use of Lorentz factor. For velocities very less than the speed of light, Galilean transformations can be considered to be a special case of the Lorentz transformations, where gamma is nearly equal to 1 and vx by c squared is fairly nominal. Hence, with little discrepancy, it can be inferred that t is equal to t prime in such cases. The Galilean transformations also hold a strife with Maxwell's equations. If we were to use Galilean transformations to predict the speed of light in different reference frames, we would find the speed of light to be c in one reference frame, as c plus v relative in other, and c minus v relative in another. Albeit Maxwell had later proven that speed of light remains constant in a medium in all reference frames. If we were still to falsify this assumption, we would find the Maxwell's equations in an unnatural and unappealing form. Lorentz transformations are, however, invariant under Maxwell's equations.